Hello, everyone. Thank you for joining the GeoScience and GeoEnergy webinar of today, 22nd of October 2020. These webinars are hosted by my colleague and friend Sebastian Geiger at Heriot-Watt University and myself from TU Delft in the Netherlands. We are especially grateful to our keynote speakers who have supported this initiative, and to you all for joining us and combat work from home isolation. Please do subscribe to our channel and help us spread the words. Let's meet each other 1 hour per week for a geoscientific and geoenergetic subject. Also, we would like to remind you about the Tea Time Talk series run by junior researchers for everybody, also junior researchers who could volunteer to share their research, especially if you are a PhD or postdoc scholar. That would also help you establish your professional network as well. So without any further ado, let me move to the talk of this week. We are grateful, happy, pleased, and honored to have our good dear colleague, Professor Jef Caers, with us today. And thank you very much, Jef, for being so early up today in California and accepting our invitation. All of you would agree Jef wouldn't need any introduction, but I would still read a few lines out of courtesy and respect, and then we will start the talk. Jef is a professor at Stanford University in the School of Earth Sciences. He received his master's degree in mining engineering and geophysics, and his PhD in engineering from the Catholic University of Leuven in Belgium, in Europe. Currently, he is professor of geological sciences, and before also he was a professor of energy resources engineering at Stanford University. He's director of the Stanford Center for Earth Resources Forecasting, an industrial affiliates program in decision-making under uncertainty with about 20 partners from the energy industry. Jef's research interests are about quantifying uncertainty and risk in the exploration and exploitation of Earth resources. Dr. Caers has published in a diverse range of journals covering mathematics, statistics, geological sciences, geophysics, engineering, and computer science. He was awarded the Vistelius Award by the IAMG in 2001. He was also editor-in-chief of Computers and Geosciences for 5 years actually. Jef has received several Best Paper Awards and written 4 books entitled Petroleum Geostatistics, he published that with SPE, Modeling Uncertainty in the Earth Sciences, which was published by Wiley-Blackwell, Multiple Point Geostatistics, Stochastic Modeling with Training Images, with again Wiley-Blackwell, and Quantifying Uncertainty in Subsurface Systems, again with Wiley. So these 4 books are quite major contribution apart from his groundbreaking work and papers that you can easily find in his Scholar page. Jef was awarded the 2014 Crumbain Medal of the IAMG for his career achievements. It's hard to do any justice for someone as grateful as and dear to all of us as Jef. Just a few lines. I hope you got a good clue, and please do visit his page and read his papers on diverse subjects, as I mentioned earlier here. Without any further ado, I would like to just ask him to start the talk. It's our pleasure and honor to have you, Jef, here with us. To the audience, please note the lecture would last about 30 minutes, about half an hour, and then followed by questions and discussions like before. Please type in your questions in the chat room and Sebastian would chair the discussion. Do not wait until the end of the talk. Please do post your questions anytime you feel appropriate. That might also trigger other questions by the other audience as well. So thank you once more, Jef, for accepting our talk. The stage, bandwidth, the screen is all yours.
Thank you, Hadi and Sebastian, and good morning, good afternoon, everyone. and very glad to be part of this distinguished speaker series. And thank you so much for putting that together in these difficult times. So today I'll talk about sort of a protocol that I've developed over many, many years termed Bayesian Evidential Learning, where we will try to do uncertainty quantification within a decision theoretic framework. So first I'll introduce myself a little bit more in terms of our group, because of course this work is not done by myself, but our group, which was first called the Stanford Center for Reservoir Forecasting, mostly focusing on oil and gas, and that has now been extended to other earth resources in energy, water, and minerals. So very grateful to be part of this excellent group of students. So our center, as I mentioned, works in the exploration and extraction of earth resources, the decision-making that goes with it, and the modeling that is required to do so. And I think we all realize that this is going to be increasingly needed because, of course, we are living on a planet with increasing amount of people and with limited resources. So getting there to a sustainable future will require transitioning from oil and gas into other forms of energy, number one, and also, for example, battery materials, which are becoming increasingly more important. And so our group works on this problem as a whole, the decision problem, but because ultimately it is with the actions that we take is going to affect what the outcomes are going to be. But of course, we work in a very uncertain environment with very limited access to the subsurface, and so this problem is a very well-defined problem. So what is BEL? It's not because I'm from Belgium that I took this; it just came out to be that way. BEL means Bayesian Evidential Learning. As I mentioned before, it's not a method, so it's not like, say, ensemble common filter or other types of methods. It's a protocol. It's not. It prescribes a series of steps that needs to be met and standards that need to be met so that you can do this on the uncertainty quantification within a rigorous Bayesian framework. Particular methods can come in, machine learning methods, history matching methods, geophysical inversion methods. They come in at some point, but that's not the point of the protocol. The protocol is prescribing something that follows the Bayesian philosophy. And one part of this Bayesian philosophy is to learn what the problem is before fitting the data. And that's going to be a big theme. So the way I'll approach explaining this protocol is by a case study, which I think is extensive, and then talk a little bit more about why this protocol was needed and developed. So I'm going to go with this color scheme because there are 6 stages to this decision making. Of course, when you want to make a decision such as where to drill well, whether to go explore with geophysical data or drilling or geochemical data, it's always important to keep the decision question in mind. What is it that we want to predict and how our decision is going to be made? So the formulation of that problem is important, and the statement of what it is that you want to predict is important. But in keeping with the Bayesian philosophy, we're not going to just start with fitting data. If you think about Bayes' rule, then we know that the first part of Bayes' rule is to formulate the prior distribution. And the prior distribution is something very complex, and it's very something challenging to put together. It's not based on let's make a base case and then do some variations around it. It's more like really holistically thinking about what are all the uncertainties and how can we start formulating that in terms of probability distributions. The main challenge is the following, is that the models that we often build are such that in the first try at least, it's very difficult to get them to match any data. And I think anybody who's worked with real data would know that, that it becomes very difficult. And the reason often why it is difficult is because the model is either lacking some physics or complexity, or the uncertainty are too small, in such a way that it can never predict the data, no matter how many models we would generate from the prior. There's no way you can predict the data. And so when that happens, you have what is called a falsification problem, that the model is falsified. And this is very different from, say, I can't fit the model to data. It's more of a hypothesis test, and I will talk about that in extenso. So one of the challenges then, of course, is to start understanding why the model is falsified and make modifications, not ad hoc by sort of changing parameters, but making modification within the context of a Bayesian prior. And so we'll explain that as well. We'll talk also about global sensitivity analysis. So global sensitivity analysis, as opposed to, say, base case sensitivity analysis, is where we try through Monte Carlo to understand what is really affecting our predictions. This is important because it allows us to simplify the problem often. If we only focus on those parameters that really affecting our decisions and not on those parameters not affecting our decisions. Once we have identified those, we can then think about what data would be informing those parameters. For example, if you had data such as production data, well test data, but they're not informing any important parameters, then forget about that data. And so that also simplifies the problem. And so we come here to some kind of a value of information assessment. So then comes really fitting data within this realm and fitting data within a Bayesian framework. And you notice that fitting data comes almost at the very end of the problem. It's not something you would start with immediately. And then, of course, we can do posterior falsification, sensitivity analysis, and decision making. I'm not going to go into that part. There's just no time for it in this half hour. So let me explain this protocol. As you notice, I haven't mentioned any methods with a case study that we just finished and submitted to SP Journal. It's a case in China as a visiting student from China University of GeoSciences with what is called a metamorphic reservoir. So this is a hard rock reservoir. Of course, it's fractured. And so, so it's very challenging to start modeling that. And in this reservoir, you see here, we have developed this area. Now we want to develop this area. And so you see that these are kind of these buried mountains with a oil column and a water column. And of course, because we have already data, there's extensive gas, oil production, pressure data that is available. So what is the question? The question in this particular case is to drill additional wells and to find out what are best positions of these wells and what would be, for example, the best time to do gas injection in order to enhance production. So, and these are typical questions, of course, that are happening in the development of reservoirs. If you would be in an appraisal setting and you don't have production, then it may be also what is the best position to drill a well to gain more information about the volume and reducing risk on volume, thereby or by reducing uncertainty on volumes. So here, of course, we're looking at a flow problem. So this is the challenging part. When you look at, if you go just look at the data and you start thinking about the problem and the properties that need to be modeled in order to get there, then we know, of course, there are typically the structural issues, the petrophysical and lithological issues, and then there are the fluid issues or uncertainties. So this table, you don't get there right away. So this table is saying, let's think about all these properties. Of course, in this case, we need to think about fracture density and discrete fracture networks, faults and their position uncertainty, their transmissibility uncertainty. As you notice, there are a number of faults in this system, of course. And then you have to think about what are the various elements. So, for example, if you're doing petrophysical modeling, then you probably are going to use at some point geostatistics. And if you use geostatistics, you need a variogram. And this variogram, if you have only 5 wells, it's very uncertain. And so you need to make some guesses of prior uncertainty. And this is often this could be based on physical constraints. could be based somewhat on data that you have, could be based on your expertise, on analogies that you may have. The issue here is that to settle on a table pretty quickly, because it's very likely that this table is going to be changed, and that's the important part, is how we're going to change this table once something goes wrong. So of course I'm not going to go into all the details of the setup of how this fracture modeling was done, and these are typical exercises that many people do, and Sebastian and others have worked on this. So yes, this is, everything is considered, and that's the important part. Everything is considered. You see that this list is huge. It's probably even only a partial list. Just some notation is that in the Bayesian world, we're going to have a prior distribution, and basically this is the prior distribution. That could be correlations between parameters. It doesn't really matter. You have a very extensive prior distribution. So with your prior distribution, we can then generate models by drawing samples. We'll show that in a little bit. Those are extensive amount of models, probably thousands, through Monte Carlo. And then we can do two things, which is we have data. For example, if we have geophysical data or we have historic data, then we can run forward simulators to predict the outcomes of the data variable, we call that. Some people call that simulated data. I'm using more of the probabilistic kind of notation. We can also, however, predict the future. For example, if you want to say what is the cumulative oil that is going to come out of the next 10 years, or what if I place a well over there, what is that production rate going to be, then I can also simulate that, and there will be then the prediction variable. So typically when we build models, we use a kind of a Bayesian net work where there are certain hierarchies in how models are built. That means once I have the fishes, I can do the picture physical properties. I have to combine that with fracture properties, and fracture properties themselves are complex and multi-scale. They exist at the fault system, at the discrete fracture network system, and even at the matrix system. And so you have to create this kind of architecture to do that. And once you've done that, you can run Monte Carlo. And so that by itself is kind of challenging for an annoying reason, is that many software don't allow for a full Monte Carlo. They only allow for Monte Carlo and specific things. So here we're varying everything at the same time, and that is really important. So we're varying the lithology, the petrophysics, we're building discrete fracture networks. We have fracture densities that can be estimated from geophysics, and their own uncertainties, fracture permeabilities, fall positions and uncertainties. So you see that you can generate many realizations from this prior. So these realizations, it's very important to know that they may match some data. For example, well data, it's easy to match. Maybe some constraints to geophysics, but they may not match other data. In particular, production data is one of them. And so then what you get is, if you simulate all of this, then basically you get simulated data versus the observed data. So it looks like these gray curves are capturing this red curve, the data, but we need to investigate this much more carefully than that. And that is the step that I think is somewhat new in this protocol, that is not often done, and I think is actually the crucial step to making a proper uncertainty quantification, that is falsification. So falsification is a deductive way of reasoning. It's not saying let's take a model that fit data, but let's see whether or not data can reject any particular model assumptions. And so the model assumptions are basically all of this. These are all your model assumptions. It tells you what the model complexity is. It tells you all the details of it. It tells you the uncertainties of it. And so what we're now going to do is use data to try to attempt to reject it. And so the way it works is it works in a coherent statistical sense through hypothesis testing. So hypothesis testing, as you know from maybe your statistics classes, is where you say, I want to, for example, I think these two means of these two populations are different, how do I test that? You assume they're the same, and then you try to reject it. And so, in other words, that is a hypothesis test. Now, the way it works here is that we're going to assume that the data is part of the population generated by the prior. And so then we're going to try to reject that. And so if you cannot reject that, then we can say that the prior is not falsified. It doesn't mean the prior is right. This is always a problem in probability, is that if you make any probabilistic assessment, there's no way of telling it whether it's right, of course, until you get the outcome. So if you do that, one way to visualize that at least is to start doing what we call dimension reduction in the data variable space. So dimension reduction is basically saying, I take all this data and all this data together. You can put it all together or all separate per well or per fluid. It doesn't really matter. But you create some kind of a dimension reduction. And you can use any technique, multidimensional scaling, principal component, kernel principal component. It doesn't really matter. What you map is you map all the gray curves and the red curve into a lower dimensional space. And so right away, you see that you have a problem. For example, the data here is the red dot, and this is the population of the prior. And so you have a problem in the sense that the prior is not covering the observations. So what you have now is a prior, despite all your hard work, with your big table and all your models, it turns out your prior is falsified. And so another question is what to do. What not to do is to try to fix it by changing parameters and thinking it's there and I changed this and that. It's really important to understand what is happening. So how do you create understanding? One way to create understanding is global sensitivity analysis. So global sensitivity analysis is saying, well, I have created all my models. This is the input. And I have created something on the output, which is some response. In our case, this is the production response. And I'd like to understand what in the input is impacting the output. But we're not doing sort of a base case scenario analysis where we build a model and perturb parameters a bit. Remember, we have all these 1,000 or few thousand of models that are generated by varying all parameters together. So this joint variation is important. And that is what is called global sensitivity analysis, or Monte Carlo based sensitivity analysis. There are many methods to do that. So Ball methods, Morris methods. The one we use is one I think that works really well for our kind of problems, where you have only very few simulation models that you can run, say a few thousand at best. The way it works is that you take your data, right, this data here, and you map it into a lower dimensional space, which is this lower dimensional space. And then you find grouping. For example, imagine you have two groups. So let's look at the red group and the blue group. With each dot, we have a particular model. And so with that model, you have a parameter, for example, fracture aperture. So that means that each dot here, we have fracture aperture. And so we can calculate the CDF of fracture aperture in this group, which would be the red, and CDF of fracture aperture in this group, which would be the blue. And so what you notice is that we see a difference from the prior. So that means essentially that this parameter, fracture aperture, is sensitive to the production response. If those CDFs would be on the same black, the red, the blue rely on the same black, then you have essentially no sensitivity. So then there's a lot of processing with that. So you can now look at all your parameters and make this plot, this Pareto plot, that tells you which are the most important parameters. So here you see we have many parameters. Here's fracture aperture, matrix permeability, oil density, and then here's fault transmissibility, water-oil contact, etc., etc. So as you go down, you can also see bubble-borne pressure, some kind of variant parameter, rock compressibility, etc. They seem to be not impacting. So of course, what you're interested in is impacting parameters. So if you have impacting parameters and you can look a little bit about also at what are these impacting parameters. Are these fracture-related parameters? Are these lithological parameters, petrophysical parameters, etc.? So what we see here, these are mostly parameters to do with permeability. And so what this indicates is that if anything, if I'm going to change this parameter a bit or even a lot, it's not going to impact any production response. So we can forget about these parameters to be the major problem. Another way of looking at this is to go back to the lower dimensional space and make this plot here. So this plot, remember, is each dot is a production response simulated from a model. And this is the data, and this is fracture aperture colored. So what we notice is that indeed, this is all blue, right? This cluster here has yellow into it. So it means that since fracture aperture is indeed important to impact and response, and it seems that if I increase the uncertainty on fracture aperture, then I would maybe potentially be able to match observations. You say, well, this is only in 2D. What if you have higher dimensions? Well, if you have higher dimensions, we do this with what's called the Mahalanobis distance, which is a distance in high dimension, where we measure the distance between a dot here and a dot here, maybe in, say, 50 dimensions. And then the outlier detection method, which is called the robust Mahalanobis distance detection method, is one that can compare your observations to your models in this plot. So for example, if your data is really very far away from all the models, then of course your data is an outlier. So you all agree here, and this example is obvious, that the data is an outlier. And if the data is an outlier, as I mentioned before, that means the prior model is falsified. So this has given us some insight into what the problems are. And so the first thing now to do is to change the prior. And if the prior is falsified, there's only really 2 or 3 ways to change the prior. What we can do is narrow uncertainty. What we can do is shift uncertainty. What we have to do is either increase uncertainty, or we have to add model complexity, or we have to do something of both. Because the prior is too small, it's too narrow, it doesn't capture the solution, so we have to increase the coverage. And so then, we have identified, for example, fracture aperture being an issue, probably that parameter is not uncertain enough. And then also we looked at other hypotheses. And so then the question is of testing these hypotheses. And so in the testing of these hypotheses, you would go through the same workflow when you generate Monte Carlo models until at some point, by adding more complexity and adding more uncertainty, you increase this cloud of points. And you see now that with this new prior, the table has been extended, parameters have been increased in uncertainty. We find that we have now a population of priors that can predict production. So good. So now we've done all this analysis, we understand what's happening, and we also understand that we can use Bayes' rule because the prior is now a valid prior in that sense. And so there are now things you can do, which is to reduce uncertainty or quantify uncertainty and thereby fit data. And there are 2 ways of doing that. The first way is the more classical history matching way. The other way is, I'll talk about that later on. So the classical history matching way would be, say, well, we first take our data, we reduce uncertainty by historic data and thereby fitting the data. And once we have the models, we can then predict anything in the future. For example, placement of new wells and whatnot. This is not always possible because, as you realize, this table is huge, right? And so there's so many parameters that are uncertain. And so if you want to do rigorous Bayesian inversion, we have to do Markov chain Monte Carlo and basically perturb all these parameters jointly. And this is, for many cases, just not possible. So there are alternatives that we've developed, which is called direct forecasting. It's where you forget about the model, and instead you try to predict the future from the past directly. And we'll talk about that in a bit. And this method is really good for cases where model inversion is just becoming horrendously challenging. Okay, so that's what I was saying. Now, Bayesian inversion, you have to also worry a little bit because there are many techniques, but the most rigorous one is Markov chain Monte Carlo, right? You have a prior, you have a likelihood, you do posterior. There are approximation models such as ensemble-Kalman filter, where you make assumptions on the model such as Gaussianity, linearity, and then you apply those into non-Gaussian nonlinear problems, but it's not really a fully Bayesian method. The one I'll talk about, which I think is quite useful, is the approximate Bayesian computation in combination with statistical surrogates. So what is approximate Bayesian computation? So approximate Bayesian computation are also called likelihood-free methods. So you're not going to have a full likelihood distribution. Instead, what is actually very simple is to say, generate a model, calculate the distance between the model and the data, and accept the model according to some threshold, and then do that many, many times. And so there are some proofs that show that if you do that, then you will get a proper posterior distribution. But of course, you understand that, first of all, the rejection rate is going to be very high, particularly when you have a lot of data. And secondly, is that each time requires running the simulator, which in this real case may take several hours. So what we instead are going to do is to build a surrogate model, and so a machine learning model that, using the information that we have, is to predict the mismatch to the production data that we have. So in other words, we have a whole set of parameters: fracture aperture, fault transmissibility. We build a machine learning model not to predict the flow output, but to predict the difference in flow output with respect to the observation. So we're predicting the mismatch. Well, why is that useful? Well, if we have a model that can, a machine learning model that can directly predict the objective function, then we can run this model millions and millions of times. And maybe of those millions and millions of times, we can then select those 1% best fitting. Then once we have that 1%, and this may be, say, 1,000 models, then we would run the actual simulator. So here you see that with our gradient boosted tree model, we get a pretty good correlation between the predicted, the true distance, the actual, which is from our Monte Carlo simulations, and the predicted mismatch. So once you have that and you do that, then suddenly you get everything, right? Is that you have models, and the uncertainties on sensitive parameters have been reduced. For example, aperture, right? You see aperture is now big. This is the prior here, the blue line. This is the posterior. And you have that for all the parameters, for all the 150 parameters that we had in this case, and then you're also matching observations. So you notice that in this history matching, there's no iteration. This is pure Monte Carlo, which is nice because Monte Carlo can be, first of all, can be parallelized. So you can run, if you have 100 nodes, then you can run 100 models at a time. And the second one is that all your models are drawn from the prior. There's no modification you're making to those models. It's not like you're going to change probability somewhere and update it in that sense. Okay, so let's now think a little bit about why it is that I came to this particular protocol. And I've written more of a philosophical chapter in this Handbook of Mathematical Geosciences, which is about Bayesianism. So what is Bayesianism? Where does it really come from? So I think many of you heard about Thomas Bayes, and Bayesianism, basically, Bayes' rule goes back 250 years. But Bayesianism is actually quite new. It's only about 50 years old. And it comes really from a history of science where people were reasoning from empirical fashion to induction to deduction. Then Popper came by, and then the paradigm principles came by. So this philosophy of science is, how do we think about science and how do we think about uncertainty? And so the key part is that if you look at this problem of the billiard table, which is the problem that Thomas Bayes looked at, is say, imagine you have two balls. Imagine you are a player, and imagine you go into the next room, but you don't see the billiard table. And so somebody throws a ball, and this ball lands somewhere on this billiard table, and this is, say, over here. And so we're telling you, you're in this other room, says there's a ball that lies somewhere on the table. And now I'm going to throw another ball, this ball O, and if this ball O lands on this part to the left of ball W, you win. And if it lands on that part, you lose. So now imagine you want to get best out of 6. Or no, get first to 6 wins. So you remember, you don't see this table. You have no idea. Only the thing you know is there's a billiard table that's flat and you have balls. And so imagine right now that the score is 5-3. So you have 2 players, you're 1 player, somebody else is another player. What is the probability you'll win the next one? The only rigorous way to solve that is Bayes' rule. Because you may be very tempted to say, well, I've won already 3 out of 8 times, so my probability is 3/8. Well, that's actually not correct, because you don't know what the probability is. So you have to randomize over all possible outcomes of that probability, and the only way to do that is Bayes' rule. So this is also what we need to do in our world, because in our world we tend to say, you know, I see the porosity in the well, I estimate the porosity of the well, it's 10%. That's the porosity of the system, plus or minus something. It doesn't work like that. Obviously, we have to hypothesize that porosity can be quite far ranges depending on the depositional system and whatnot that you have. So important to know that if you want a proper uncertainty quantification, at the end, you have to use Bayes' rule. Why is that? Well, what was found is that humans don't think like that. And there are these very famous persons who got the Nobel Prize for economics who found that most humans, even very intelligent people, resist Bayes' rule. They want to do it very differently. And they use their own logic and their own reasoning about uncertainty. And so what they realized is that if people do that, then you get answers that are completely incorrect. And so that's why I think I designed this protocol, is to say, let's do this in a proper fashion. And let's say, what are all these steps that are needed in order to adhere to the philosophy of Bayes' rule, of Bayesianism, and at the end, actually apply Bayes' rule to do an uncertainty quantification. I just want to mention rather quickly and finally that this is not only applicable, obviously, to oil and gas, but in our consortium, we work on this for water and minerals, and also geothermal energy. Geothermal energy is quite important in the United States in the Basin and Range, which is in Nevada, which is kind of sitting that way from me, where we need to drill exploration wells in order to understand whether there's enough heat in the system. So the problem, of course, with geothermal is that this heat is quite deep. You need about 150 degrees centigrade to, for viability. But your exploration wells can only be perhaps 1 kilometer deep before you start drilling real deep production wells. And so the question is, can we predict, viability from these exploration wells? Now, the problem is physically quite complex, is that meteoric water is raining onto these mountains and then getting into the subsurface, percolating. Sometimes you see hot springs, but because this is a sedimentary valley, often they're covered, and so you don't see anything. And so then the question is, how do we explore? So to do that, we have to, again, build models, and models have many uncertainties. In geothermal, there are obviously structural uncertainties. The faults that are there, and the rocks are consisting here of very hard rock, basement rock, and then the basin filled with sediments. And of course, in geothermal, we have very little information. There's no seismic, there's only gravity, magnetics, and so there's a large uncertainties on all these properties. So then you can build models, and what those models would predict is the temperature distribution in the subsurface. So obviously, if you know the temperature distribution, then you know whether you have viability. And this is a viable system here, because you see that the temperature is welling up the heat is welling up along this fault, creating a higher temperature around 150 degrees. So this is good. But of course, there are many models you can build, and they are so complex with so many uncertainties that inverting those models with respect to existing temperature measurements and running the physical flow simulator in console all the time is just impossible. So what we instead do in this direct forecasting, and this is what I want to show here, is that instead of building models that match data, we will try to use the data. So here we see the actual temperature data as it decreases in depth. And this is the simulated data, and this is the simulated forecast. So this forecast is not matching these observations yet. But you see in the forecast that we can already start classifying certain models as unfavorable, right? It's cool at the top, and certain models that are favorable where there's heat at the top. So what I'd like to understand is not build a relationship between the models and the predictions, but directly build a relationship between the observations and the predictions. So we want to establish this relationship. And so now we run into the realm of machine learning and deep learning and other techniques, is where you say, if I have this data set and I have this data set, this is images and these are curves, how do I predict one from the other? And so many strategies in deep learning or machine learning involve dimension reduction, involve trying to map it with sufficient layers of the neural network into a linear problem, and then solve the linear problem. And that's kind of the approach that we took, is using machine learning techniques to eventually map the problem into a linear problem. So on this one axis, you have a reduced dimension parameter that comes from machine learning that represents the data variable, and this is the prediction variable. So now I can predict in lower dimensional space directly the prediction. I don't have to invert the model, and once I have that, I map back into the real world, and I get prediction of temperature directly. So this is what you get, is you use your data to directly predict posterior distributions of temperature. And you see then that in many cases you get favorable, but there's still a few cases where it's unfavorable. Okay, that's all I got to say. Just want to point out that a lot of this information about the protocol is in the book, the Wiley book, which came out in 2018, Quantifying Uncertainty in Subsurface Systems. I have also a YouTube channel with lots of course material that, I have a course at Stanford that is this particular course. It goes through all the details of some of the things I talked about. And then also we have lots of Python scripts, because I start to realize that much of what we do is interacting with other softwares, so Petrel or Eclipse or console physics or etc., or open source softwares, and we build basically scripts on top of them to do all this work. Well, thank you much for listening. I hope you got something out of it.
Thank you very much. I was quite absorbed to the story, didn't realize that we have actually passed the time by 15 minutes already as well. But really very nice. It was very, very interesting and inspiring lecture. Without any further ado, Sebastian, please, we have plenty of questions already.
Yes, posted. Thank you very much. Thank you, Jef, for a really nice, really interesting talk. I've plenty of questions myself, because you get into the philosophy of what you need to model and how you want to model things. Let's hand it over to our audience. So in no particular order, I start with Andres Valdez. It says, around slide 18, you mentioned you can add uncertainty or add complexity. If adding uncertainty, you add on the entire input parameters or only on the relevant uncertain parameters?
Yeah, you would mostly focus initially on the impactful parameters. Those are most likely to have an effect. Now, it may be, of course, that you have taken a parameter, let's say mean probability, and you vary between 100 and 101, then it's not going to have any impact regardless. So you have to be a little bit careful. The other thing you have to be careful about is that, and I didn't go into that, is that uncertain non-impactful parameters may interact with impactful parameters. So the effect you create is by this interaction. And so our methodologies in our global sensitivity analysis allow you also to discover these interactions. Because you always think about main effect, and but there's also interacting effects, which are very important. But excellent question.
Thank you. A question from Soren Pop, nice talk. The models discussed involve many parameters. How expensive, in terms of computational resources, is it to estimate the impact of each parameter separately?
So the main effect, the global sensitivity analysis is free once you have the Monte Carlo. So you do the Monte Carlo and you have all the models, and then what you get is this DGSA, distribution error sensitivity analysis, that takes just a minute to run. So what you don't want to do, however, is freeze all the parameters and vary one. That is not Bayesian. That is something else that may work in certain circumstances, but for uncertainty quantification, you have to be careful with that, because that parameter may still be interacting with other parameters, which is required for in our Monte Carlo.
Thank you. Just see that one of our former speakers has posted a question. So Andrew Curtis, Andrew, good to see you. Thanks for giving a talk a while back on similar topics. So he comments, nice talks. In nonlinear uncertainty quantification, uncertainty on physical characteristics changes dramatically if you change the parameterization. This undermines risk-based decision-making. How might we overcome this?
Yeah, that's a deep question. Let's take a minute on that one. So what this says here is what the challenge remains is that when the prior went through a falsification test, you're not in the clear. And that your comment is alluding more to, we still need really experts to say, okay, is this a reasonable physical model? And the nonlinearities are going to perhaps make changes that are unpredictable. A statistical technique will have a hard time discovering that. So the physical expertise is very much needed. It's also very challenging still, of course, with a limited amount of Monte Carlo runs to discover all of the variability that is there. But we unfortunately live still in the time of limited computation time, that it is still, this protocol is also a practical protocol, because while we cannot solve all the questions perfectly, it does solve some questions, and there's still always room for improvement.
Thanks. So Laila Hashemi has a question again, thanking you for the talk. How should we decide what parameters to change and study the impacts? Due to computational resource, we cannot study all parameters' impact on the output. And she continues, says, related to the test case in China, you showed aperture and matrix permeability play major roles.
Yeah, so when you look at the sensitivity analysis output, right, as I said, it's about learning from Monte Carlo, but it still means that the expert has to be involved. So if you look at your sensitivity analysis and everything on the hot side is permeability and everything on the cold side is porosity, then you have a clue what's going on. And I think that's what the sensitivity tells you. There's something wrong with permeability. And now permeability can be many things. Relative permeability, fractures, matrix. And so then it's about really understanding. For example, the thing that we saw in the China case is that our pressure of our data went down much faster than the pressure of the simulations. So that's the second derivative in the PCA, but you have to still realize that, okay, I'm missing permeability because the pressure is going down too fast or fast enough. So still need to have your engineering expertise involved. It's not magic.
I think it's an important point. It's not the history matching, it's learning about what the reservoir is doing. Kishan Kumar has a question. Great presentation. Would reduced order forward systems like multi-scale models give similar sensitivities for the cases that you studied?
I would use reduced order things in surrogate modeling. So as you notice, I use surrogate model not to approximate functions, but I use it to select from prior interesting models, right? So because if you're going to use reduced order, then there's always the question, are you removing physics? That's important. And when you look at this fracture case, there's so much physics happening that I rather use a reduced order model to say, if this runs fast, this runs only a minute, and the other model runs 3 hours, I can do Monte Carlo with this one and then evaluate with the other one. I think that's a great strategy overall.
Thanks. And I think that sort of answers the question we had from Yuan Wang, which is a two-part question. And thanking you for the interesting talk. He asked if you can share your idea about, instead of conducting forward modeling with complex parameters, if it's not sometimes better to work with simpler forward models, but be more rigorous on uncertainty quantification.
Yeah, I agree with that. I think there's a lot of, when I present a case study, it all looks like, okay, that came onto the screen, in 3 days. It's not. We all know that. And so, first of all, there's the juggling with Eclipse and Petrel. But I always suggest exploration first. Running lots of models quickly rather than saying, I'm going to build my best model and then worry. I think it seems like building a lot of models, even if they're not right? You get insight, you learn. It's about learning. And it's not about magical tricks and softwares that give you an answer. It's really about you learning from the experimentations that you're doing. In a way, Bayesianism forces you to be a scientist. Right? It forces you to experiment and learn and fail and then go back and redo. So yeah.
I think that your comment about just building, just sort of having a shot at your very best model, that chimes well with when Mark Bentley gave his talk. He said quite often, because we have these big computers, we build very big models. At the end, we end up understanding two things, or not knowing, don't understand two things: the reservoir and the models. We have two problems. Right. Rather than just one problem. So yeah, being approximately right rather than precisely wrong, there's a lot of value in that. Lots of questions still coming in. So Moitaba Noruzi has a question asked, could you elaborate please on the part where you said about how most people try to vert from Bayesian methods when assessing uncertainty?
Yeah, so there's a number of examples in the book, and the Undoing Project, I highly recommend reading that book. It has enormously wonderful examples. For example, imagine that you're in a room and there's say 100 people in the room, and the average weight of people in that room is say 65 kilograms. And then a person walks in, and that person weighs 40 kilograms. And they ask people, what is the average weight of a person in the country? So now you have 100 samples, and then one sample comes in. So what people do is they overestimate evidence. So if something comes in, new data, suddenly they forget about the prior, right? Because we have 100 people, there's a prior, that means that estimate is uncertain. And so in order to update the uncertainty, you would use Bayes' rule, right? A very good example of this is in the studies of COVID. There was a study published by Stanford professors, which has been retracted. He was not a statistician, and he said the problem of estimating death rates in COVID. And so if you go out and sample, you might find death rates that are very different from what the actual death rates are. And there's a lot to do with the fact that you're estimating very small numbers. So this is another problem where people often make mistakes, is when you have a small sample size, they overestimate the evidence you're getting as new samples are being added. There are many in this book, many examples like that, and I highly recommend reading some of those. Very insightful.
Great, thank you. Just if I can sort of sneak in my own question here quickly, because it is along those topics that you've just discussed about learning, dealing with uncertainty in the data. So quite often data itself is uncertain. We may have drilled wells in preferentially high permeable productive zones, so we underestimate how natural growth or how large non-permeability regions in the reservoir are. So how does your approach help dealing with a lack of clarity, the uncertainty in the data itself, not just the conceptual model of how we interpret the things in the data?
Yeah, that's a good question. Didn't touch on that. That becomes part of the prior uncertainty. So because in Bayes, everything is parameterized, so your data uncertainty has to be parameterized as well. And if it's parameterized, it has to go into the Monte Carlo. So what Bayes suggests is that if you have data uncertainty, is that you have to simulate data sets. And each data set then becomes part of this set of the prior in Monte Carlo, on which you can then go on and do your studies. So in other words, it's just part of the prior. For example, if your production data has much error, the way we'd handle that is generate multiple production data sets by drawing from the prior distribution of production data sets, so to speak, and then do history matching with each one of them. This is how the Bayesian framework I would recommend. Yeah.
Thank you. So a very practical question from Muhammad. Been great talk. Have you done anything related to uncertainty in CO2 sequestration? Is that something in your books?
No, I've done groundwater. In the book, it's groundwater, geothermal, oil and gas, and reactive transport contamination. But CO2, similar problems. Of course, need to predict something. You have data. You have to build a model. So yeah, look into that.
So perhaps that's probably the last question, given that we're reaching 4 p.m. UK time, 5 p.m. in the Netherlands, and you probably want to have your breakfast now, Jef. Hamid's question is a bit longer question. So thanking you again for a very interesting talk. There are many subsurface applications where data is limited or very expensive to acquire. He continues, says, in those scenarios with not a lot of data, do you see advantages in using surrogate models for selecting priors, especially when trying to avoid overfitting? Any advice on how we can deal with this difficulty?
Yeah, there's many cases. The geothermal case is one like that, right? There was not a lot of data. There was only 2 temperature wells or 3 temperature wells. That's what you have. Some gravity data, which didn't tell you a whole lot. Magnetic. There's other cases, exploration, of course, where you have very few data. In that case, I think, as you mentioned, it is important to more think about sensitivity and value of information rather than saying, I'm going to make a rigorous uncertainty quantification, because you have so little, right? And then it's more about what extra information would I get and how would I determine that? And so the information you would get is that information that is reduced as much as possible, some impactful parameters. And that can be studied. That can be studied through simulation, which has been done for 4D seismic, but other things. Through simulation, you can understand what the value of information would be if you would go and acquire it. And I think for those cases, that's more what you're looking at rather than sort of rigorous uncertainty quantification.
Great. Thank you very much, Jef, for the talk, for answering all these questions. Thank you to the audience for the great question. I hand over to Hadi for some closing remarks.
Yeah, thanks very much from my side too. It was really, I learned a lot. I would like to take the chance to introduce our next week's speaker. The next week's speaker would be Professor Kamini Singha from Colorado School of Mines. Kamini will speak about the importance of surface water and groundwater connectivity in a critical zone context. So until next week, the same time, stay happy, healthy, and tuned, and we see you all next week again, the same time. Thanks very much, Jef. It was really a fantastic talk.
Thanks for having me.
Thank you, everyone. Bye-bye.